трансляция у нас не включается. А, вот может она сейчас и... А? Да вроде должна быть. А вы не могли посмотреть там, что с ней происходит? С трансляцией? Нету? Нету? Есть, да? Можно начинать. Окей. Спасибо большое. Okay, sorry for some technical delay. Today we are restarting our lectures on the modern dynamical systems, and I just recall you that at the previous lecture we completed the first part of the plots that we wanted to cover. Namely, we finished our introduction into hyperbolic dynamics. We studied the purposes of geodesic flow on oriented surfaces, and we learned that the flow is necessarily ergodic, learned something about its symbolic representation. Namely, we understood that it's closely related, especially if we deal with the modular surfaces, that it's closely related with continued fractions. And we also established a Nosov property and used it to get some more information about the dynamical properties of the geodesic flow. So we switch into a new part, huge chunk of the modern dynamics that we would like to cover at the current course. And we are starting the part about interval exchange transformations. That I will usually mention by the famous abbreviation EETs, and translation surfaces. So it's a very different dynamics in some sense, because we leave the warm and welcoming world of hyperbolic dynamics, and we go more to a parabolic world. At the same time, it's something which is very similar to what we already studied, because we will continue to live in the world of surfaces, flows on these surfaces, and so on. So the plan is the following. There are a few things that I want to outline while we are studying this subject. Namely, I would like you to understand the connection between these things, the kind of a discrete combinatorial model given by interval exchange transformations and the topological model given by translation surfaces. I would also be happy if you will learn how it's related to billiards and rational polygons that we mentioned briefly on one of the previous lectures. The second part is to study the standard list of questions that we already announced in connection with geodesic flow. Namely, we would like to understand, is it true that typically we deal with minimal ergodic or uniquely ergodic dynamical systems, or here things are organized in somehow different way? And the third part will be about the modular spaces and their geometry and dynamics. And I hope that we will have enough time to complete our study with some conclusions about the results that were obtained recently in the 21st century by a few outstanding mathematicians, some of which were the Fields medalists like Arthur Avila and Maria Mirzakhani. But before we arrive to the 21st century, we're gonna start with some history that was initiated in 60s, much earlier. So let me first recall you something that you already know from the previous parts of our course. We take a two-dimensional torus, and we keep it with a flat Riemannian metric. And the vector field. And I would like to ask a few natural things from this vector field. Namely, I want it to be unitary and parallel for that metric. So in such a case, we can think that our torus is nothing else but a factor of the R2 over the action of some lattice. So T is isometric to the result of factorization, and this lambda is a lattice, and I want to choose a lattice in a way that this vector field that I fixed on T corresponds to the vertical vector field d dy on the factorization. So our vector field corresponds to this one, to the particular one. It's the same thing as to say that you fix some direction on the plane and then you try to glue a surface using this plane. So then I can associate the Teichmüller space. So Teichmüller space means that we want to classify. I will give all the definitions later when we will study it in a full generality. But at that moment, I just mean that we consider the diffeomorphisms. And we classify them modular diffeomorphisms isotopic to ID. So isotopic to the identity. And so this is given by GL to R. It means that we consider the space of lattices equipped with bases. And then if we consider a different classification of these pairs, mainly that we consider the classification model as a full diffeomorphism group, it's an homogeneous space that we can obtain by factorization of GL to R or GL to Z. So this is our modular space. Please keep in mind this elementary picture, because we will use it later in two contexts. On the one hand, we're going to generalize it by replacing torus by some more sophisticated surface. That's what I'm going to do now. And at the same time, when we will study homogeneous dynamics, we will also live in these homogeneous spaces constructed in a similar way, but not necessarily with these particular groups. So we are interested in the dynamics of the vertical vector field on this factorization. And so we want to classify these pairs. You have a pair with you have a torus and you have a vector field. So you know that this torus is isomorphic to this the result of factorization, but so you would like to understand how many pairs in some sense you can get, how many different pairs. So it depends on how this isometry is given and then how it agrees with the choice of the vector field. That's more or less what you have. So we are interested in the dynamics of the vertical vector field on the R2 factorized on the lambda. And so it's very easy to analyze it through the return map to some geodesics, we will choose it to be to be transversal. So we want it to be not vertical. So we take a return map to a non-vertical, closed, oriented geodesics. And what is the geodesics on such a surface? The geodesics on the torus, how do they look like? I hope you understand. And so you may think about it that basically you took a circle and you make a natural parameterization on it. So you can consider it to be, okay, here there was a t, 2-dimensional. And this would be a 1-dimensional thing. So it's a result of factorization of r over z. So after rescaling the time, we may think that we return to some circle. So you understand what I mean, that instead of studying these dynamics, we can reduce it to the study of the dynamics of the first return map to some transversal, to the geodesic we choose in this way. But this return map is something that we understand what is it, right? When we get a torus and we look at the vertical vector field, so we take a first return map on some geodesics, what you get, it should be just a rotation on the circle, right? So we can think about it that this return map it's a rotation on the circle for some alpha. And then we already discussed this map. We started our study basically from this map. And we know what happens. We can have all the answers. We know that this rotation has everywhere dense orbits if the parameter is not rational. And we know that if it's rational, then the orbits are closed. We also have the answers about the question about ergodicity. You remember our first lecture and then the list of problems I gave based on it. So it's ergodic, and moreover, it's uniquely ergodic. So that's the rotation and the corresponding dynamics given by a vector field are uniquely ergodic. So we have the full list of answers on the questions that we consider challenging and interesting. And now I want to generalize all the constructions I made here to the context of more general surfaces. So I want to take some class of surfaces for which I can get the description in terms of homogeneous dynamics, for which I can get the description of the dynamics of the flow given by a vector field in terms of some maps that look as a generalization of rotation on the circle. And I want to understand what kind of information I can get through this construction. That's our plan. Now let us describe first the list of the surfaces that can be covered in this way, that can be considered as a generalization of the torus that we started with. So I take a surface. I will assume that it's compact, orientable, topological surface. Maybe it will be useful to fix its genus. Now I have to fix some non-empty finite subset of points. Since I said it's finite, I can enumerate them. There will be S elements in this set. And then with each point, I will associate a natural number. So it will be a vector given by the integers. And these positive integers will be the ramification indices. And I will add one more requirement, because the choice of ramification indices should agree with the choice of the genus. Namely, I want the Riemann-Roch formula not to be violated. So I will explain in a moment. I will put the structure and I will explain. The idea is the following, that I would like to have a surface that would be flat almost everywhere except the finite number of points. So when we deal with the tori, we had a flat metric, but it was very easy to have it because the genus was equal to 1. So the Euler characteristic was 0, and we were not supposed to have any singular points. But if we deal with a genus that is higher than 1, then the Euler characteristic starts to be negative. And so in this situation, you cannot put a flat metric everywhere. There should be some exceptional points. Otherwise, there is a contradiction, because you can integrate the curvature and get 0, but you know that the Euler characteristic is negative, right? So you should have some exceptions. And these indices are responsible for the topology around these exceptional points. They tell us how does our surface look like around these exceptional points. So morally, how many leaves in the cover we need to put. Like, what is the angle defect, if you want, when we go around this exceptional point, in order to keep Gauss-Bonnet formula true and all the differential geometry constructions true. So now we have to give a formal definition. So what does it mean that we fix the structure of the translation surface? So we keep this triple. We have a surface, a list of exceptional points, and their indices. So we can, the structure is simply a maximal atlas. That's what you studied when you dealt with manifolds, right? So you fix the maximal atlas. I will denote it by zeta for the complement to the list of exceptional points. And this atlas is formed by charts And what do we want from these charts? We want, on the one hand, that any coordinate change is simply a translation. Locally, of course. So that's what guarantees us that we have a flat structure everywhere except these particular points. And then we need to say what happens around these points. So for any I that is between 1 and S, we can fix a neighborhood. This VI will be a neighborhood of AI, our special point. So we fix a neighborhood of AI, and we fix a neighborhood of 0 W, so it's a neighborhood. And the ramified covering. Pi. That takes my VI into WI 0. So this ramified cover is of degree ki. And so it's done in a way that any injective restriction of pi is a chart of my zeta. So what it gives us? Let's think a little bit what the definition means. So we mean that we basically everywhere have some flat structure. So we go from one chart to another one just by translation. And around special points, we have like several leaves, one under above another one. And so we have ramified covering. And this ki is responsible for the ramification index. So it's the degree of this map. That's how it works. What does it give us? Why we are so happy to have a picture like that? First, we can think that all the surfaces we deal with are oriented already. We can consider only, we start with orientable surface, then we choose orientation, and then we always work only with structures that are compatible with this chosen orientation. Then we have for free the volume. Since we have a Riemannian surface, we may have a volume, the form that will be responsible for it. Now I insisted that since we have these translations, then we are given for free a flat metric on the complement to this exceptional set sigma, right? So the metric exhibits a true singularity at each AI. And there we have a total angle around AI will be equal to 2 pi ki, right? So it's a total angle around AI. So this is the price we have to pay for the fact that on the one hand we want to have high genus, and on the other hand we want to have flat metric almost everywhere. And then we have an area form. So this area form can be smoothly extended from this part to the singularities. Of course, on a flat part it's elementary. Then what happens around the singularities? It's simply this one. dx dy. Hope it's visible what I wrote. And the very last point, but not the non-important for us, it's the point on the geodesic flow. We can describe it quite explicitly in this situation, because we can first define it with respect to the flat metric that we have on the most part of our surface, and then we can extend it to a one parameter family of constant unitary directional flow flows on this set that behaves nicely, and then we can extend it to these particular points. And in particular, this family of flows includes vertical and horizontal flows. So we have a lot of dynamics. We can ask ourselves what's going on with these flows, with their properties, and so on, when we have flows on the translation surface. What else? Apparently, due to the fact that our surface is equipped with a complex structure, we have also a very important protagonist, which is called the one form. So we have a holomorphic one form, And this one form is simply dz in every chart. But it doesn't vanish on the complement, so at any point at AI, what do we have? This one form has zeros, and it has 0 of order k minus 1. So we have a holomorphic one form that far away from singular points looks simply as dz, so it doesn't vanish. But in all the special points, it has zeros, and the order of zeros is given by the ramification indices. And since there exists a Riemann-Roch formula, we can be sure that this star equality is satisfied if we have a thing like that. So more or less, what can we conclude? That if we fix the structure of the translation surface, then we determine a complex structure on our surface, and additionally we have a holomorphic one form with prescribed zeros. And conversely, if you give me a surface that has one form described like that, and then I can recover enough information to define a translation surface. So there is a kind of a duality. How can I recover the charts if you give me a one form? Very natural question, right? You have a surface and the one form, there is a complex structure, and you want me to provide you the structure of the translation surface. It's very easy to understand what to do around the singular points, but how to use this one form to restart the chart. And the charts are simply obtained by local integration of this one form. That's it. So we described a kind of a dual language where the first half is about description in terms of the atlas, and the second half is a description in terms of the one form defined on the surface. We're going to use both. So now I want you to understand the following important thing, that these surfaces, maybe it appeared to you as something very unnatural because we introduced it in a way that we put on a surface many additional structures. However, it's not true. On the one hand, it generalizes what's going on the torus, but on the other hand, you can see it while you are playing billiard, when you are studying one of the most natural dynamical systems. So I would like you to understand the connection between translation surfaces and the billiards in rational polygons. We already talked a bit about billiards, but I will recall you some general ideas. So we take, at the very beginning, some bounded, connected, open subset, whatever. In R2, and we call it U. But since I would like to restrict myself to billiards and polygons, I will not consider what I drew here. I will consider only the areas that are bounded by line segments, because I want it to be a polygon. So instead of such a U, I will consider a polygon. And when I say rational, okay, my polygon is nice enough to have finite number of sides. I don't want to deal with some infinite situation. And when I say rational, I simply mean that all the angles of these polygons are rational number multiplied by pi. Then I can consider the compactification of U and I also can consider the closure. So sometimes we include the boundary, sometimes not. It depends what we want to understand. One important thing that maybe you already heard about the fact that very often we use some kind of how to call it properly, unfolding procedure for the billiards. So now I will give a formal description, but morally what we are going to use is simply a symmetry when we will follow the billiard trajectory. In billiards always the geometric law, the geometric optics law is respected, but instead of reflecting the trajectory, sometimes it's better to reflect the whole table. So we will use this tool. But how can we describe it formally, algebraically? We can fix the side of compactification, and we can consider the orthogonal symmetry that has the C as an axis, and we can consider the subgroup generated by this symmetry, subgroup of orthogonal maps. And if my billiard is indeed rational, so all the angles are rational numbers, then I can be sure that in rational polygons, G is finite. Moreover, we can even describe it rather precisely. I don't know how important it is, but maybe it makes sense to be sure that you can give not only informal picture, but also a formal definition. So what you can think is the following, that if you fix the smallest number such that all the angles of your polygon are given by Pm divided by n, so it's the smallest number that can, such that all the denominators of your angle divided, then this G is a diagonal group of order 2n. And it's generated by the rotations of order n and the symmetry sigma c. What does it mean that we have a translation structure? How can we find it if we deal with a billiard? Why are we sure that we have a translation surface? Let me explain. So we take G as an element of our favorite group, and we consider a chart constructed in this way. So we had a pair, then we apply G, Z, and that's how we get the coordinate. Now, what are these special points? This is how do we get a chart. And now we need to explain what happens around singularities and who they are. So if we consider a side of our polygon, and we consider the image in the closure for any point, then we may consider the intersection of a small ball, for radius epsilon, where epsilon is small, intersected with u. And we can take V as a connected component such that Z0 belongs to V. And then we consider the interior of the closure of the image of V in U hat. Anyway, this map will work as follows. So we take this G sigma C, and we consider the map to R2, where it takes ZG and sends it to G of Z. And then when we have Z G sigma C, we consider G sigma C of Z, where sigma is a affine orthogonal isometry. So then we have a chart from the neighborhood of ZG in M onto an open set of R2. So what does it mean geometrically? We wrote a lot of formulas trying to be accurate algebraically, but maybe it was just confusing for you. Well, geometrically it's much simpler. Let me tell you informally what we do. We start with a polygon, and as I said here, we will not reflect the trajectory, but instead we will reflect the whole billiard space, the table. And we will continue in this way. And if we know that all the angles are rational, then we can be sure that if we wait long enough, we will get just a translated version of the original polygon. So that's why we care so much about the fact that we need this rationality, because otherwise every time you will get a new polygon, and you cannot guarantee that you will arrive to the moment when you have just a the result of parallel transportation of the table you had at the beginning. But if angles are rational, that's what you get. And after what you do, what is written there in such a known way is simply that you identify the sides that are parallel to each other. So you glue them. You remember always that every time you reflect at the table, you mark which side goes to which side. And so by the end, you get a series of polygons, and you can associate the sides of these polygons with each other, and then you can use this picture to glue the surface. And what you get, obviously, will be a surface which is flat almost everywhere, because just before you started to glue, you had an absolutely flat picture. Your picture was at the plane. At the same time, there were some exceptional points, and these points corresponded to the corners of your billiard, of your polygon table. So then some of these points, they were glued, so you just need to control what kind of ramification index you get in this way, because you know how to calculate the total angle defect. And so what you get will be a directional flow on the translation surface, while you were starting from a billiard flow in the rational polygon. Now we are ready to comment a little bit who are the interval exchange transformations. Maybe I should just summarize it, saying that we can describe explicitly the relations between the trajectories of the billiard flow, and they are in correspondence with the geodesics on our surface, if we exclude from the consideration these particular points. Now I told you that the block is called interval exchange transformations and translation surface. So I introduced you to the word of translation surface. I hope that I explained you why do we care about translation surfaces. There are at least two reasons. On the one hand, it appears when we study billiards in rational polygons. On the other hand, if you were given a surface with a one form, then you necessarily have a translation structure on it. And this second option happens sometimes. For instance, when you are studying the measured foliation on surfaces. So there are at least two reasons why do we care about the directional flows on the translation surfaces. But we are still missing the definition of interval exchange transformation and the precise description of the connections between these two notions. So I proceed with it. So interval exchange transformations. Let's start not with the definition of the subject, but once again from the translation surface. As we agreed, we need to know several things about translation surface. We need to fix the surface itself, the list of singular points, their ramification indices, and we fix a chart. So we take one particular constant vector field, which is defined by our chart. Let me say that x So we define the notion of the separatrice. We will distinguish those who are incoming and those who are outcoming. Separatrix for x, it's simply an orbit of x that ended or started at this marked point, at this list of exceptional points. And the connection, it will be an orbit that connects two marked points with each other. So it's an orbit of x, which is both incoming and outcoming separatrix. So the separatrix is an orbit of our flow that finishes or departs from the marked point, from a singular point. And if there is a connection, it means that there is a way to connect two marked points by the same orbit of our billiard flow. It doesn't mean that they necessarily exist. It's just if they exist, we call it like that. So let's take a point, the singular point. I claim that if Ki is its ramification index, then we necessarily have Ki incoming separatrix and Ki outcoming. Now let me take a transversal. I will call the transversal just an open bounded geodesic flow, geodesic segment, such that no singular points belong to this transversal. That's why exactly I use the word transversal, that it's in a general position with respect to the marked points. So it's an open bounded geodesic segment. I want to exclude these non-trivial points from the consideration, and I also want it to be transverse to my vector field. I will parameterize this simply by arc length, so natural parameterization. Now look, we consider the directional flow. The directional flow is definitely area preserving. So if I consider a first return map to S of the flow generated by X, what can I think about this? First point is that why should we be back-ended? Why we can measure the first return? Maybe we will never be back for many points. This can never happen. And why it's true? Because we can ask Poincaré and he helps us. What Poincaré said? He said that if you have a measure preserving transformation and you have a set of positive finite measure, then almost all points should go back to this set, right? So in this situation, that's what exactly will happen here. That X was an area preserving. And thus, Poincaré recurrence theorem guarantees that Ts is defined on dTs of S, where dTs is a set of full measure. Now, what can we say about this TS map? We know that this dTs, the set of points for which we will go back, it should be an open set. And I claim that this dTs will have only finitely many components. So there are only finitely many options for the return time. So we say that dTs is open. And we claim that return time is constant on each component of dTs. And that dTs has only finitely many components. And before I explain why it's true, I will just provide you a picture so that you can visualize what does it mean, what TS looks like. TS works like that. It takes this set. I will pretend that it is defined on the whole interval because we agreed that almost all points go back, so we can ignore those that do not. And then we divide it into several parts. And points who lived on the same part, they go back together. So these guys went all together, these guys went all together, these guys went all together, and in each connected component, my map is nothing else but just a translation. just an isometry. So Ts restricted to each component of dTs is simply a translation. Why we are supposed to have only finitely many components? So let's take a component. We denote it by G. And since it's a component, it is supposed to have endpoints. And assume that X is just a point which is an endpoint of some component. So now we can say that Tg is a return time to S of the guys from component G. Then there are several options what may happen. One option is that there exists a T between 0 and Tj such that the orbit of our flow X starting at this point which is non-capital X stops at time T at the point sigma. So it could happen that some of our points arrived to the singular points. And it happened before we returned. So if there exists such a T, that the orbit of X starting at X stops somewhere in a singular set without having crossed S. This is the first option. So it's a kind of a black hole. If we arrive here, we stop here. So we chose the way that is based on separatrix. If we are not choosing, it's like, here's Dona, выдачи нет. So if we arrived here, we are not continuing. And then it means that we did not come back. Another option that could happen to us is that this thing never happened. But what does it mean that it never happened? It means that the orbit that started at our point X, it's defined up to the moment when we are back. And then, since it's a moment of our return, we know that the end of this orbit is also belonging to S. So we came back to S without having crossed S before. So what does it mean? There are not so many orbits that are passing through singular points, right? So if this was an endpoint, what could happen? That the guy who is next to us the very close point is supposed to come back on a different time. But it doesn't happen unless we are separated by some separatrix. But separatrices are limited in their amount because we need to pass through the singular point. That means that this moment when the return time changes happens only finitely often, right? And the reason why it's true, because if we take a point which is very close to our point, then they're supposed to share their destiny unless there was a singular point that divided them. And if it happened, then okay, it's possible, but then the singular point, they are controlled, and so it happens only finitely often. Otherwise, if it did not happen, it's impossible to imagine that two points that were not separated by the separatrix, they have different return time. So So we understand now that we have the picture that I presented here, and these points that correspond to the change of the return time, they are exactly those that are in one-to-one correspondence with those who go to the singular points. So formally speaking, what our interval exchange transformation look like? So we have a bounded open interval. And we have a map. And this is a part of our bounded interval, and this is a part of our bounded interval. And this map restricted to dt is just a translation. And those who are not in dt, there are finitely many points. So what do we need to know to fix our interval exchange transformation? We need to know the number of intervals. We need to know their order, and I will call it with permutations. And the permutations will be written in the following way, that you give names. For instance, here, 1, 2, 3. And then I check in which order do they appear here, 3, 2, 1. And so I will have the guy who is responsible for their order on the top, and the guy who is responsible for their order on the bottom, and they jointly give me a permutation. And now, what I do is that I also need to fix the length of the interval. So I will have a vector of length. A few words about the history. Interval exchange transformations, they were born at some point in 60s, as I already said, 60s, in the Soviet Union. And it's very hard to say more, because apparently they were discovered several times by different brilliant mathematicians. And more or less the story was as follows, that Vladimir Arnold was thinking about exactly the picture that we started with. The situation when you deal with a torus and you consider the first return map to the translation for the direction of flow, and you get a rotation on the circle. And he said, okay, and what happens if I consider not 2 intervals but 3 intervals? The picture we have here. So this is a way to think about interval exchange transformations, that they generalize the rotation of the circle. At a similar time, the full definition for abstract number of intervals was given by Valery Asiledets, who at that time was a student of Yakov Sinai. And he was motivated by the following fact, that he wanted to consider the object that is similar to translation surfaces and the measured foliations on surfaces. And at the same time, Anatoly Katok was thinking about rather similar subject, because he was studying billiards. So many people arrived to the same construction. And at the same time, people, say, in the United States were thinking about a similar thing, because Thurston made a classification of the foliation on surfaces. And so he also noticed that he needs something like that, and so on and so forth. So it's a very natural object, but it's very hard to say who are those who created it formally. And I will need a few more notations. We will use them more later, maybe on the next lecture, but it's good to fix it now. So first, it's a translation for every interval. So we said that we have a length vector. Now we fix a translation vector as well. And we may think that in order to define the translation vector, we can say that we multiply the length vector to a matrix. And it's very easy to see that this matrix is antisymmetric. It will be a very important matrix for us in the future, But today we just introduce it and leave it in peace. Maybe I should make an example to make it more explicit. I will in a second. P is a permutation. P bottom and P top, there are two lines that give us the order of the intervals on the top and on the bottom level. So how does this vector look like? For example, here we look at the first interval, and the first interval is translated on lambda 2 plus lambda 3. The guy number 2, we need to first to subtract lambda 1 and then to add lambda 3. So his translation is given by lambda 3 minus lambda 1, these kind of things. Yeah, I just tried to make it more explicit. How do we compute these deltas? And that's the corresponding matrix. So this is the guy, delta is the guy who is responsible for translations. So let's see. For example, the guy number 1, he's translated on lambda 3 plus lambda 2. Because the leftmost end of the first interval is translated on the sum of these two persons. The destiny of lambda 2 is more sophisticated. You need first to subtract lambda 1 and then to add lambda 3. And the guy number 3, he simply lost these two steps, so you have to subtract lambda 1 plus lambda 2, right? So that's what is written in that matrix. Now, we would like to define the suspension for interval exchange transformations. The idea is that we agreed that if you have a translation surface, then we can find interval exchange transformation as a first return map to the segment of the transversal for the directional flow. But the question is it true that we can do the inverse way as well? So if I give you an interval exchange transformation, do you know how to construct a translation surface such that the first return map on some transversal gives you exactly my interval exchange transformation? And the answer is affirmative, and we will provide the two different constructions, and sometimes we will use one, sometimes another one. So this is the next goal, to be able to construct a translation surface if we were already given interval exchange transformation. So it's our way to duality, to establish duality of these two languages. So actually, it's not enough to know just the interval exchange transformation. We need some supplementary data. Namely, in order to fix the surface such that this translation surface will satisfy these conditions that I want, we need also to know the return times. We need to know how long it takes to come back. So let me fix the interval exchange transformation. And we take tau. And we say that it's a suspension vector if a few requirements are satisfied. So it's a definition. I want it that the sum, this will be positive, while the sum of this will be negative for all k between 1 and d. For almost any permutation, almost any now doesn't mean anything precisely mathematically, but for most part of them, we can construct such a vector. And before I do that, I explain what I want to require from the permutation. It will be the requirement that we want to hold for the rest of this part when we discuss interval exchange transformations in this course. So we agreed that we need to fix a permutation, and we will be interested in, as we said, in some dynamical properties of the original dynamical system given by the flow on the surface, or equivalently on the first return map. And one of the requirements, one of the conditions in which we are interested, one of the properties, is the property of minimality. I recall you that we are interested in the situation when there is an almost everywhere dense orbit. However, imagine that your permutation splits into two independent parts. For instance, you deal with a case when 1, 2 alternate and 3, 4 also alternate. This is very bad for us, because if there is a kind of iron curtain between two parts, it means that you cannot, even if you dream about it, construct an everywhere dense orbit, because every orbit will live on its half where it was born. So this should be forbidden. If we want to have some non-trivial dynamics, we should forbid all the permutations that split into two independent parts. So we will say that we will consider only irreducible permutations. And this one is called reducible. Be aware that it's not the reducibility you are used to when you are studying algebra at the first year. In algebra, it's much more sophisticated property. You need to think about cycles and so on. Here, we simply forbid them to split into two independent parts. So, if you are given an irreducible permutation, then there is a candidate for tau. There is a way to construct a suspension vector. So this canonical tau is given by p bottom alpha minus p top alpha for all the letters. Alpha here means the letter, the name of the corresponding interval in interval exchange transformations. In this example, we have a 3 letters alphabet, and so alpha can take a value 1, 2, or 3. If you have more intervals, you have more diversity in this sense. So p bottom minus p top, and I claim that necessarily this tau will behave well enough. But it only works if the permutation is irreducible. But if the permutation is reducible, then you simply cannot find such a suspension vector. It does not exist. So now I am going to describe two constructions. They're related to each other, but they look quite different. And I will start from a simpler one. The idea is as follows. You always assume that the permutation is irreducible, and you consider vectors. Their horizontal component is, we live on R2, but I will very often interpret R2 as a C, as a set of complex numbers with a real and imaginary part. So my horizontal components, the real part, is given by the length. And my imaginary component is given by the tau, that is a suspension vector. For instance, you can take this one, but it's not, of course, the only choice. And I then consider a polygonal line. So what I do, if I want to draw a picture, let me still use the 3 intervals, is that I fix some vectors. For instance, this one will correspond to the interval number 1. Then there is an interval number 2, for instance, like that. And an interval number 3, like that. 2, 3. So now I try to do this chain of vectors. 1, 2, 3. And now I make the same chain, but using the bottom order. So I try to make this one parallel, then I do this, and then I do this. And both lines, they have the same endpoints. I can, if I use these canonical values for tau, it's not that hard to check that if we started at the same point, we will arrive to the same point. And then both halves leaves on, they lie in the upper or lower half planes. And since they do not intersect except for the endpoints, then their union is a Jordan curve, and so we can construct a translation surface. And the way how we construct it is very natural. We just glue to each other the parallel sides. Of course, I will have a flat structure here, because as you can see, we live on the flat plane everywhere except the finite number of points. These points correspond to the vertices. And the only thing that is important in this context is that we should understand that some of the vertices, they are glued. So it's not true that you have as many singular points as the number of vertices of your polygon. For instance, we start with this point. This is a point number 1. And this is the beginning of the vector number 1. It will be glued to this point. But this point, it's also the end of the vector number 2. And then it's also the start of the number 3, but this we agree. So these 3 points are in reality the same point. And the same is true here. It's the end of 1. The end of 1, the end of 3, the end of 3, beginning of 2, beginning of 2. So we have 2 singular points in this case. And we have a surface which is constructed by gluing the parallel sides. So this sigma is simply the image of vertices. And the chart comes from the fact that we can put everything on the plane. So this is the first approach, how to see that if you are given an interval exchange transformation with irreducible permutation, then you can always construct a translation surface such that the first return map for the vertical flow will give you the same interval exchange transformation as you started with. The second construction is harder. It will require more effort, but we will be able to use it in a more active way for the future constructions. So I think I will describe the second construction and then we make a break, okay? The second construction was introduced by William Beach in early 80s, and it's called zipped rectangles. I will write a lot, but then I will make a picture that hopefully will make it more explicit and illustrative for you. So we start with the inter-exchange transformation with its vector of length and permutation. And as before, we want to define tau and zeta, which is lambda plus I tau. So here we identify R2 with C, with a set of complex numbers. And I recall you that we have translation vector. And so I will also introduce H that will be constructed as follows. And the theta, that will be delta minus H. So it's sigma tau, not zeta, on our chart. So here I interpret lambda and tau as raw vectors. Zeta is also a raw vector, but of complex numbers. And delta and H, they are column vectors in R alpha. And so theta is also a column vector. So H alpha, who he is? He is the sum of tau beta, where beta is selected with the condition that pt beta is smaller than pt alpha. And then we have to subtract tau beta, where p bottom beta is smaller than p bottom alpha. So we added some conditions, the suspension conditions on theta. So we can be sure that due to these suspension conditions, H alpha are positive. It's very important for us. Why it's true? Because if you look here, it's the first sum of the, it's almost everywhere positive, except the situation when it's 0, and it's 0 when pt alpha is 1, because we cannot put here any beta. And if you look at the second sum, which has minus here, so we consider this part, it's almost always negative, except the same moment when you have 0. And then, since we assume that it's a reducible, it never happens that you have zeros in both. You always have 0 either on one or in another one, because if it's true, then you would have p top alpha equal to 1 and p bottom alpha equal to 1. But it's not possible, because otherwise you will have a part in one, nobody will go. You will have a permutation that has 1 here and 1 here, and so it splits into 2 parts, and it contradicts irreducibility. So we can be sure that H alpha are positive. And using this fact, we will construct the following rectangles. So we take RT alpha, it's ET alpha, on 0H alpha. Who is ET? IT alpha. It's the corresponding interval of interval exchange transformation. And the same T means top, the same you do with bottom. So these are singularities of T. And then it also matters, you remember my picture. It also matters who are the singular points on the bottom level. So we will also write them. They are singularities of T minus 1. And we constructed this R, and we will also need S. ST I and SBI. And STI given by singularity multiplied on T alpha. And here it's the same, but you take singularity for the inverse map. Now it's probably time to make a picture. I will make it for the situation with 4 intervals to make it a bit more exciting. So this is my zeta A, zeta B, zeta C, zeta D, and here will be zeta D, zeta C, zeta B, zeta A. That's what we did in the first construction. And now we start to build this R. So we start with, this is my R, TA. This is the second. This is the third. And this is the fourth. And here it will be a similar thing. Something like that. So this is, do we have a color chalk now? Yes. This is my R, TA. This is C0. Then there is this C1T, C2T, C3T, C4. And then here we have C3B, C2B, C1B, and we have RAT, RAB, and so on. And so each rectangle is a result with the same letter is a result of translation. Chick, 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 chick. Here, here. There is a translation among them. They have the same size, the same length of the sides and so on. And then we consider our future surface as a union of all these elements. And so we get it as a first return map when we use this construction. I think here we make a short break. After I will explain how to see ramification indices from this construction, and we will try to apply it to understand why it can be useful. So let's make a break. Дальше уже никогда не заканчивается. Okay, so let us go back a bit to these constructions that we made. I hope it's quite transparent. How did we proceed? So we gave the precise values for this H alpha. We constructed the rectangles, and these arrows are supposed to make it more visible for you how do we identify them. And also, maybe you see it here, that there is this surface that we constructed before, given by the zeta vectors. So now you see the connection between these two constructions. And now let me write it up formally. So we start with M hat. It's a union of all the elements we introduced before. So it's RT alpha, RB alpha, STI, SBI, C0, CD, CTI, CBI. The definition for the C is written on the left, and we also add S star. S star is this part. It's a closed vertical segments whose endpoints are UD0 and CD. So it's this one. And what we see is that we can identify RT alpha and RB alpha. They are in one-to-one correspondence. RT alpha plus theta alpha, so it's just a translation on theta. We can say the same about C, that CT PT alpha is in one-to-one correspondence with CB PB alpha. CT PT alpha plus theta alpha. And the similar thing is true if we consider PT alpha minus 1. So if the T alpha is positive, then we can identify by theta PB minus 1 D the top part of SPT PBT with S star. PT PB minus 1 D. And if it's negative, then here we have top. If it's negative, we would have bottom. So we will call M what we get as a result of these identifications from M hat. So M hat is what we have on a flat way, and now we start to glue things together. And M is what we constructed while gluing like that. And then who is sigma? Sigma is given by all our C's. Of course, as before, we identify them because we glue some of them together. So formed by C. So it's not a hard exercise to check that M is compact. And that if you remove sigma, then you have a topological orientable surface. At the same time, the return map of the vertical vector field is exactly T, and the return time is exactly H. So we have to, we may see that we can complete this construction by investigating the local structure at these singular points. Okay? So do you follow me what happens? We try to, let me make it more explicit. So we want to construct a surface using interval exchange transformations. As we discussed already, it's not a unique way how you can reconstruct the surface from interval exchange transformation. And one of the options, how can you fix the picture and make it more canonic, is when you fix the return time. So you fix how much time it takes to come back to your each of your intervals. What does it mean to do that? I can start with this suspension vector as we did before, but then this is a translation vector, and then I can construct a vector H in this way. And due to all the restrictions we put, we can be sure that H necessarily has positive elements. And so what we do after, we use this H as a height of the corresponding rectangle. What does it mean that it's zipped? So the idea is the following, that you have these rectangles and you glue corresponding rectangles to each other. But you put the points that were vertices of the previous construction, you put them on the border between two rectangles. And why it's called zipped? We understand zipper, it's molnia in Russian. So you can open this construction here up to this point. So this point is exactly the point that we used in the previous construction as a vertex of the translation surface. So we will open it, and one part will go to this direction, and another part will go to that direction, to another rectangle. And then we glue rectangles to each other. Yes, of course. You glue the sides of rectangles. And you use this identification. So you know that they are the result of the translation of each other. And so you do it in the way that if you started, so the plan is the following, that you want your interval exchange transformation to be the first return map. So you start like here, you go up to this border, and then you continue here. Because you have to be back to this interval, to A interval. So in order to do that, you need this part to glue to this part, then that part to glue to this part to glue to that part, right? So that's how you will glue it. But you will not glue the whole side. You will fix these points as written here. And so you're gonna, and then you're gonna glue it, so you will be able to open this construction here. And so that part can go as A side tells it, that part will go as B side requires, and then you open it up to here, this should be fixed. Okay? So what it gives us, why it's considered cool. We already had the first construction that was basically simpler. The idea is the following, that it allows us to control, if we fix these heights of the rectangles, it gives us a chance to control how much time it takes to come back. You know that you need first to cover this H, and then to continue this, and then you are done. You are back to your interval. So it will allow us to make a more uniform construction, and we will use it later while describing the Teichmüller flow. Because just keep in mind now that in this construction you fix the return time to the interval. Not only the order in which intervals return, but also general return time is also fixed. So we discussed everything except what's going on in the singular points. So let us go to this part, discuss the ramification indices and the ramification numbers. So these singular points are given by C, as written there. CIT, CBI, 2D minus 2 elements. 2D minus 2, why? Because these endpoints are fixed, so they are not included. Now we can consider a map that are turning around points of sigma in an anti-clockwise manner. And so we know what it does. We go from one singularity to another one, because we know how we glued them. So it works almost everywhere except the positions when we are at the end of the interval. So in this case we have the situation when this one is simply 1. So we know that sigma Cti is Cb, Pb, Pt minus 1, 1 minus 1. And here it's the same, just we have to exchange 1 by d. So first thing is that what we notice is that sigma is a permutation. Second thing we notice that every cycle of sigma has even lengths. And the last thing we notice is that our ramification index is exactly the half of length of the cycle. So those who belong to the same cycle, it's exactly those who will be glued in our procedure. And so we need to count all the angle defects from them. And so it will be given by the half of length of this cycle. So we know that d minus 1 should be the sum of the kg. And thus we know that since we already discussed that we have this corollary from the Riemann-Roch formula, then we know that d is 2g plus s minus 1. So if you are given the number of interval exchange transformations and you need to estimate the possible genus of your surface that you will construct making the suspension procedure, then you should satisfy this condition, and S here is the number of singularities. So you see from this formula that you cannot have more than d plus 1 divided by 2, but definitely you may have less as a genus. It will be important for us in the future because this genus will be the border of a possible number of ergodic measures for interval exchange transformations. So it will tell us how many ergodic measures we may have, and it will tell us in each situation what is the diversity of measures, not only something topological. Now, using this construction, we may comment on homologies and cohomologies of the surface we built in this way. This will be the next subtopic that we want to discuss. I will not erase my picture because I will use it later, but I think I can erase the previous. So homologies and cohomologies of M. So first we consider the first homology group. It has rank 2G. Then we may consider a similar thing, but instead of M, we take M minus sigma. We want to exclude the singularities. So the rank will be already 2G plus S minus 1, but we just learned that it's equal to D. It's true also for H1 M sigma Z. And there is a, you know, in homologies, there is a way to write exact sequences. So also here we can do a similar thing. And we can say that we have H1 M minus sigma Z. Then we have a map onto to H1 MZ. And then we have the injective map to H1 M sigma Z. So it's an exact sequence. And a zipped rectangle construction provides us a natural basis for this guy and for this guy. So how do we do that? We fix the index, the interval with the corresponding number, and we can consider theta alpha. It will be the image in our homologies of path joining the interior in the interior of M hat, the center of each rectangle, R alpha top to the center of RB alpha, bottom alpha. You remember we had this theta as a translation, so we just fix a particular number in each, consider the vector that is responsible for this translation. And for other points, it's the same vector because you make a parallel transportation, so it's not forbidden to do this. And you may have a similar thing, fixing zeta as a connection for singular points. So the intersection form in homologies establishes a duality between these two groups. How does it work? You consider the intersection form, as you always do for the cycles. And you say that it's on the surface, and you say that it's delta alpha beta. And this is the basis of the first group, this is the basis of the second group. And so that's what we have, and we establish the duality between these two groups. But at the same time, this theta alpha can be interpreted as the basis of this group as well. It's just a curve on the surface. So it's nothing else as a member of a group of the first homologies. So you can consider it as a class of the first homology, and in such a case, you can consider the intersection form between theta alpha and theta beta. And apparently, what you have as intersection form will be something that we already saw. It's a sigma beta alpha. You remember who was sigma? It was this antisymmetric matrix that we used to produce the translation vector from the vector of length. And I told you that we have to keep in mind this antisymmetric matrix because it will be important for us. So what is cool in this construction is that this antisymmetric matrix is exactly the same that you get as an intersection form in the group of the homologies with integer coefficients. So it's nothing else, and this matrix has a very deep topological sense. The matrix that looked completely technical for us when we considered interval exchange transformation without connection with translation surfaces, right? So it looked just as some technical way to describe what exactly our map did to the points, to the intervals. It apparently has a deep topological sense, that it's the intersection form in homologies. And so, due to this fact, we can also go to cohomologies, use the Poincaré duality, and then establish the connection between the one form that we already mentioned discussing the complex structure on the translation surface with these technical things about interval exchange transformations. So how do we do that? We transform this exact sequence in homologies into exact sequence in cohomologies. So they change their order, the places. But this is still injective, and this is onto. And so who is this holomorphic one form? You consider it as a, you can integrate the holomorphic one form you had for translation surface, and it will define you an element in the group of cohomology. And so in a similar way, you can say that the intersection form this is a zeta A, and if you consider the image of your one form in H1 M minus sigma C, you have that alpha, so you can see lambda and T as an elements and the area of translation surface, what is it? Here, for instance, we're going to use the fact how we constructed zip rectangles, because we constructed our translation form from our translation surface from this rectangle. So we can compute the area, right? It's just 4 rectangles. So you just need to sum up the lambda alpha H alpha products. But what does it mean? It means that you have tau, these forms that we discussed, multiplied by lambda. So that's how you can construct the area of your translation surface even without keeping in mind the rectangle construction. You can express it immediately in terms of tau and lambda. So, okay, so we discussed a little bit the topology, and now you may ask me that you want to be back to dynamics finally. So in the remaining of time, I will say a few words about the first property that can be considered as a first step in our plan to establish all the ergodic properties of interval exchange transformations or on directional flows on translation surfaces. And so we want to ask ourselves about minimality. I will show you 2 approaches to this question. One is a topological one, as we did with surfaces and so on. And another one will be pure combinatorial one. So let me start with the topological one. So it's about minimality. And connections. So what happened in the case of torus? When the vertical vector field has a rational slope with respect to our lattice, then it's clear that a short enough horizontal segment will not intersect all the orbits. And what we're going to see now is that a similar situation may take place also in a higher genus. First, we do a very stupid thing. We take 2 tori. Each of them is a result of factorization on some lattice. We assume that both lattices are non-degenerate in the sense that you don't have vertical lattices in it, vertical vectors in it. And so we can choose at each torus vertical segments of the same length. And then we slit Ti along AI, BI, and glue. So we glue it, you understand, you take 1 tori, you can take another one, and then you make a hole, and this hole has 2 borders, and the hole are completely identical, and now you glue this border to this one and this one to this one. You exchange them to get something non-trivial. So you get a surface of genus 2, obviously, with 2 marked points. They are images of our A's and B's that you identified with each other, so you will have marked points. And you will have a translation structure on this surface, and ramification indexes will be equal to 2. However, it's pointless to discuss minimality in a standard sense, because obviously if we do not have any periodic orbits and so on, but obviously if you take a small horizontal segment on one torus that does not intersect this interval, then we will only intersect the orbits that live at the first torus, and we will never go to the second one, and vice versa. This is exactly the situation of reducibility, if you want. So now what is our plan is to understand which translation surfaces can be obtained from zipped rectangle translation and apply it to get a better classification of possible behavior of orbits of corresponding flows. So we want to understand if this construction is kind of exceptional or it's a rather standard situation, what may happen in the case of higher gems. Let's try to do that. So we start with the translation surface as usual. We need to know the surface, the singular points, the ramification indices, and the chart. And we consider the flow. I will fix the vertical in a similar way you can denote the horizontal. Flow of vertical or horizontal vector fields. And let me start with periodic orbit. So I take a point such that this point of period t for vertical vector field. So what I want to say is that, as usual, we live like, Liverpool fans. In the situation, you'll never walk alone. So it's impossible to have a point that is periodic such that no points on the left side or on the right side that live close to this point are also periodic. This is the key idea. So I want to claim that I have a whole cylinder of periodic orbits. But in order to do it more accurately, I will state some lemmas and propositions, and then just comment informally on some of the proofs. So the lemma claims that there is a maximal open interval a bounded one. I forgot very important thing. Interval G around 0, such that for S in G, FVT of HS of X0 is defined for all times t. And we can see it, I say also that since we fix the period, that also all of them will be periodic. VVT, VHS, X0 for S is from our interval, and moreover the map that takes the point ST to the point SVT S phi HS x0 is injective. And I claim that the compact set Z plus given by lim S to supremum of my interval G FV0T FHS x0 is a finite union of sigma and vertical connection between them. And the same thing holds for Z minus, but here we will approach not the supremum but the infimum. And what we call a cylinder it's exactly what is formed by FV0T FHJ of x0. And so Z plus and Z minus is a boundary of this cylinder. So what we claim simply means that if we have a periodic orbit, then necessarily it's not unique, and there are guys to the left or to the right or both that are also periodic with the same period, and the boundary of this set of periodic orbits should be somehow related to the singular points. So unless you meet a singularity, your life does not change. It's like when we measured this return time, you remember. So if you have a periodic orbit, the orbits can stop to be periodic only if there is a singular point between them. Otherwise, they will continue to be periodic when you go, for instance, from your point slightly to the left or slightly to the right. So what should be true is the following thing. Proposition. I skip the proofs, but I hope you understand the general idea of it. And in my notes, there will be more precise technical details. So the proposition is the following: that you take our translation surface, be a translation surface, and you take a bounded horizontal segment. In your translation surface. So assume that S is such that it emits any vertical connection, if we have any. Then we have two possibilities. The first possibility is that every infinite half orbit of the vertical vector field meets S. Or another possibility is that there is a cylinder containing every infinite orbit of the vertical vector field that does not meet S. So either we have a situation when all of them come back, either if there are some exceptions, there are not just one exception, but a whole cylinder of exceptions. So we know that almost all of them come back because Poincaré told us it's true. Now, when we look at the exceptions, we claim that they do not walk alone, they go in cylinders. Or there are no exceptions and we are lucky and everybody comes back to S. That's what we say here. So now corollary from this statement. If the vertical vector field has no connection, vector field has no connection it is minimal. Every infinite orbit is everywhere dense. What does it mean to have a connection? It means that there is an orbit such that two different singular points live at this orbit. So another corollary that states basically the same thing, so this will be corollary 0 and this is the corollary 1, is that you have a translation surface, you have an open bounded horizontal segment, everything as we like. So we assume that S meets any vertical connection, if any. The leftmost point of S is in sigma. So you see, now we put it in a way that one of the endpoints is in a singular point. And the rightmost point either belongs to sigma or to a vertical separatrix. Which does not meet S. Then what it gives us? We can be sure that we know enough to fix the translation surface in the following sense. That the translation surface is isomorphic to the one constructed constructed from ET via zipped rectangle construction. So what does it mean? It means that if we choose smartly the transversal, such that the ends, for instance, will be given by singularities, and then we find the first return map to this transversal, which is necessarily interval exchange transformation, as we know, and then we apply to this interval exchange transformation zipped rectangle construction, then we're going to get the same surface as we started with. If you choose arbitrarily the transversal, you may have something different. Topologically, it will be the same, but still you may have some differences. But if you fix smartly the transversal, then you will reconstruct the same surface. What does it mean, all these things, in terms of interval exchange transformations? So first we need to interpret the notion of connection. It's a very simple thing. We just want that singularities meet at the same orbit. Two different singularities. This is singularity of t, this is singularity of t minus 1, and after some iterations of the map, they meet at the same orbit. So the statements we made now is the theorem that was proved first by Michael Keane in 1975, that if an ET has no connection then it is minimal. And there is a weaker version of Keane's condition. Is those interval exchange transformations that have no connections, they are called Keane's interval exchange transformation. And in particular, if the length of intervals are rationally incommensurable, so it's the rational dimension of lambda 1, lambda d is equal to d, then ET is minimal. Of course, here we assume that the permutation is irreducible. And in particular, this last statement means that almost all interval exchange transformations are minimal. Before we speak a little bit. No, altogether. There are no rational relations between length. Yes, so in particular, but not only. For triples, it's also forbidden, and for longer things. So one important comment is that it's a sufficient condition, but it's not a necessary condition. It's not true that if you have rational relationships among the length, then you cannot have minimal interval exchange transformation. There are many examples. Maybe the most famous among them is Arnoux-Rosy family. But it's not the only one where this condition is violated, but you can have minimal examples. However, it also happens that once you put these conditions, the rational conditions, you have almost always non-minimal interval exchange transformations. So it's still an open question to find a way to treat non-Keane's families of interval exchange transformation. What do I mean to have a way to treat? I mean that if I give you a family, for instance, I tell you that this is a permutation and the first is equal to the fifth and the sum of the second and third is equal to the fourth. You should be able with your strategy to tell me either majority of members of this family are minimal or non-minimal. And up to now, there are almost no results. All the results we have are either about some particular families, or you put some very strong condition on the type of racial relationships you may have. So if you are interested in kind of very ambitious project that is not hard to formulate, you are welcome. Here it's a place where you can apply. Now, why Keen's theorem is true? There are two different approaches how one can check it. One approach is a direct one, when you really try to prove it, looking at the interval exchange transformations. And in this case, you use once again a similar logic. Exactly, you assume that it's not minimal, so this should be a periodic orbit. And then if this orbit is periodic, then it should have a periodic neighbor, either to the left or to the right. And then you iterate this procedure, and you see that your cylinder of periodic orbits should contain on its boundary some singular point. But then if it contains a singular point on its boundary, then it's easy to see that a singular point should be periodic as well. But if it is periodic, it's a direct violation of the condition that we have no rational relationships between the length. It gives you a direct, non-trivial rational relations with the length, and so you are done. Another approach is to prove first all these statements about translation surfaces, and then extract the Keen's condition from these constructions that we made. So first let me comment on the proof of Keen's theorem. If we don't have any connection, then we can use the zipped rectangle construction, make suspension, and then a vertical vector field should have no connection as well. Because if it has some connection, interval exchange transformation would have a connection. And that if it does not have any connection, then due to the theorem that we wrote somewhere, I think corollary 0, we can be sure that it's also true for interval exchange transformations. So why corollaries are also true? We can consider them in the opposite order. First comment on corollary 1 and then on corollary 0. So for corollary 1, what happens? We assumed, maybe I should do this. So we assume this thing that the leftmost point is necessarily the singular point. So we say that then it's not possible that there is a cylinder that contains every infinite orbit of the vertical vector field not meeting S, because otherwise we will not have a singularity at the left. So every ingoing separatrix of the vertical vector field meets S. And then you look the intersection point, which is the closest to the marked point, and you see that it's necessarily also a singularity. And so you get a one-to-one correspondence between the ingoing separatrices of the vertical vector fields and singularities of your interval exchange transformation. And in a similar way, you do the same with outgoing separatrices and with singularities on the bottom level. And so the vertical lengths of the corresponding separatrix segments, they determine the suspension data. And so you see that you have isomorphism here. In a similar way, concerning this corollary 0, you do morally a similar thing, that you say that if it's not true, if it's that there is no connection, then it's minimal. If it's not true, there should be an open bounded horizontal segment such that you do not meet any infinite half orbit. Because what does it mean to be periodic? It means that it will not be everywhere dense, so you can find a piece where you do not enter with your orbit. And you can find a horizontal segment there, right? So it will not be true that every orbit intersects it. But then, by the propositions that we wrote here, there should be a cylinder of this exceptional behavior. So the boundary of the cylinder, as we discussed, is given by singularities, by separatrices. So exactly as I told you for the proof of interval-exchange transformation, the similar logic work. So I think I'm gonna stop here. Let me just summarize what we understood. I hope the general logic of Keen's theorem and its interpretation in terms of translation surfaces is now rather transparent for you. The key argument comes from the fact that it's impossible to have one periodic orbit among non-periodic ones. If you have one periodic orbit, you should have other periodic orbits, and they should form a cylinder. And the boundary of this cylinder should necessarily include some singular points. So interval exchange transformations are typically minimal, and every interval exchange transformation gives rise to the translation surface such that this interval exchange transformation is the first return map to a smartly chosen transversal, and vice versa. If you have a translation surface and the directional flow on it, then you get interval exchange transformation as a first return map. So once Keen understood this thing about interval exchange transformations, he immediately made a conjecture saying that typical interval exchange transformation should be also uniquely ergodic. This conjecture was proved several years later independently by Harvey Mazer and Bill Veitch, and they published their papers in one issue of Annals of Mathematics, because they both proved the same result, but with very different tools. And so our goal for the next couple of lectures is to repeat their success and to understand why interval exchange transformations cannot have typically more than one invariant measure, why there are some exceptions to this rule, and in general, how to understand what's going on with the invariant measures for interval exchange transformations and for the flows on translation surfaces. I think I stop here. Thank you very much for your attention.